Tonight, we are going to talk about a message. Not a metaphor, not a symbol. An actual, real physical signal. A stream of ones and zeros travelling right now, at this very moment, across 16 billion miles of empty space. Racing toward Earth at the speed of light. It left the spacecraft 23 hours ago. It will arrive at a massive radio dish in the California desert sometime in the next hour. When engineers decode it, some of what it says will make perfect sense. The spacecraft's temperature readings, its power levels, the rotation of its antenna relative to Earth, the faint, persistent whisper of plasma washing over two surviving scientific instruments, 16 billion miles from the nearest human being. But some of what that signal says has been alarming scientists for years. Because on November 14th, 2023, Voyager 1, the most distant human-made object in the entire history of civilization, stopped making sense. It didn't go silent. That would have been easier. It didn't stop transmitting, didn't freeze up, didn't power down. That would have been a grief we knew how to process, the clean, final kind, where you understand what happened and you say goodbye. Instead, it kept transmitting. Every single day, right on schedule, across the largest distance any machine has ever communicated across. Voyager 1 sent its signal home. The carrier wave arrived at the Deep Space Network antennas strong and clear. The timing was perfect. The radio frequency was correct. The signal was there. But the data inside that signal was gibberish. A repeating pattern of ones and zeros, looping over and over, like a heartbeat that had lost its mind. Like a person who is alive and breathing and making sounds, but none of the sounds are words. The spacecraft was screaming into the void, and no one on Earth could understand what it was saying. For 5 months, the most distant machine humanity has ever built was unreachable. And when engineers finally cracked the code, when they finally understood what had gone wrong deep inside Voyager's ancient computer, what they found was something that should not have been possible. A single corrupted memory chip. 3% of the spacecraft's total memory, permanently destroyed. Probably struck by a cosmic ray particle, a single proton or heavy nucleus, fired from somewhere in the deep galaxy, travelling at a significant fraction of the speed of light, crossing interstellar space over thousands of years, arriving at precisely the right trajectory to punch through a chip the size of a thumbnail, located inside a spacecraft the size of a small car, floating in the void 15 billion miles from Earth. A cosmic bullet, from a source we cannot identify, aimed at a target too small to imagine, and that the breakdown, the diagnosis, the extraordinary repair is just the beginning of why tonight's story matters. Because what Voyager has been sending back in the years before the breakdown, and what it has resumed sending back since, is far more alarming than a memory chip failure. What Voyager 1 is detecting in interstellar space right now contradicts models that took decades to build. It is measuring things that should not exist in the configuration they exist in. It detected a persistent hum from the plasma of interstellar space that no model predicted and that no one fully understands. It recorded a magnetic field anomaly in 2020 that simply refused to go away, month after month, year after year, until scientists began to seriously ask whether what they were measuring had anything to do with the sun at all. And the spacecraft doing all of this is running on 249 watts of electricity, less power than 3 standard light bulbs, using computers with a combined total of 68 kilobytes of memory, transmitting a signal that arrives at Earth measuring 1 quintillionth of a watt. 7 alarming discoveries, each one stranger than the last, each one harder to explain. Each one coming from a machine that by any reasonable engineering standard should have stopped working 30 years ago and simply refused to. By the end of tonight, you are going to understand what the most distant machine in human history is still sending back from the edge of the solar system. You are going to understand why some of what it is saying genuinely alarms the scientists who are listening. And you are going to understand why, when the last signal finally fades into the noise as it will, and sooner than we would like, what we lose will not just be a spacecraft. It will be a window onto the universe that we will not be able to reopen for a very long time. Before we begin, if this kind of exploration slow, careful, reaching into the dark speaks to something in you, take a moment to subscribe. It helps this channel find the people who need it. Now, let's go. Part 1. The machine at the edge of everything. The year is 1977. The world has no internet. There are no personal computers in homes. NASA's budget is shrinking after the Apollo program's decade of extraordinary and expensive achievement. And two spacecraft are sitting on a launch pad at Cape Canaveral, Florida, pointed at the outer solar system, waiting to begin the longest journey any machine built by human hands has ever attempted. They are called Voyager 1 and Voyager 2. Voyager 2 lifts off on August 20th, 1977. Voyager 1 follows 16 days later, on September 5th, taking a faster trajectory, which is why, despite launching second, it will become the farthest from Earth. Each spacecraft weighs 1,820 pounds. Each stands about 12 feet tall, bristling with instruments and antennas and booms. Each carries a suite of scientific sensors calibrated to a very specific set of targets: Jupiter, Saturn, and their moons. The mission, officially, is designed to last 5 years. Not 10, not 20, not 49. 5 years. 5 years of data collection, 5 years of planetary encounters, 5 years of discoveries. Then the power would fade steadily. The instruments would start freezing in the absolute cold of the outer solar system, one by one. Systems would fail. The spacecraft would drift silently past the orbit of Pluto and into whatever lay beyond, transmitting nothing to no one. That was the plan. The mission is now approaching its 49th year. Both spacecraft are still operational, both are still transmitting. Voyager 1, as of 2026, is approximately 172 astronomical units from the Sun, about 16 billion miles. Voyager 2 is approximately 144 astronomical units out, roughly 13.4 billion miles. Together, they are the two most distant human-made objects ever to exist. The Voyagers have crossed the termination shock, where the solar wind slows from supersonic to subsonic. They have traversed the heliosheath, the turbulent transition zone between the Sun's domain and the galaxy. They have crossed the heliopause itself, the boundary where the Sun's influence ends and interstellar space begins. And since that crossing, Voyager 1-inch 2012 and Voyager 2-inches 2018, they have been sailing through the very local interstellar medium, the space between the stars, sampled directly by a human instrument for the first time in history. But here is what nobody expected when they launched. The strangest discoveries were not going to come from Jupiter. They were not going to come from Saturn, or Uranus, or Neptune. The strangest discoveries, the ones still generating published research papers in 2025 and 2026, the ones that still do not have fully satisfying explanations, were going to come from a boundary that scientists had spent decades modelling, calculating, and predicting, and getting wrong. Not just slightly wrong, dramatically, measurably, alarmingly wrong, in ways that are still being unravelled today. Part 2. What scientists thought they understood. There is a boundary at the edge of our solar system. Not a wall, not a line you could see with any telescope, but a real physical threshold where the Sun's influence, its magnetism, its pressure, its constant outward stream of charged particles collides with the rest of the galaxy and, eventually, loses. Scientists call this boundary the heliopause. To understand it, you first have to understand what fills the space between the planets. The Sun is not a passive star. It is constantly, relentlessly exhaling. Every second of every day, the Sun releases a torrent of charged particles, mostly protons and electrons flowing outward from the corona, in all directions at speeds between 250 and 500 miles per second. This is called the solar wind. The solar wind was predicted theoretically by physicist Eugene Parker at the University of Chicago in the late 1950s. His colleagues were skeptical. They thought the outflow from the Sun was transient, happening only during storms. Parker's mathematics said otherwise. The Sun's outer atmosphere is so hot millions of degrees that the gas cannot remain gravitationally bound. It must flow outward, continuously, forever, for as long as the Sun is shining. Spacecraft measurements in the early 1960s confirmed Parker was right. The solar wind blows continuously, every second, every minute, every year. The Sun loses about 1 million tons of material per second to the solar wind and is so massive that this barely matters. The solar wind carries the Sun's magnetic field with it. As the Sun rotates once every 25 days at the equator, that field gets wound into a spiral pattern extending outward through the entire solar system. This magnetized bubble, inflated by the solar wind and stretching far past Neptune, far past Pluto, deep into the outer solar system, is called the heliosphere. Everything inside the heliosphere, every planet, every moon, every spacecraft humanity has ever launched except for the 2 Voyagers, is inside the Sun's domain. But the solar wind cannot expand forever. The galaxy is not empty. Between the stars there is gas, extraordinarily tenuous gas, about 0.1 atoms per cubic centimetre, in our local region of the Milky Way. For comparison, the air you are breathing contains about 10 to the 19th atoms per cubic centimetre. The interstellar medium is roughly 10 billion times less dense than air. A better vacuum than the most advanced laboratory on Earth can achieve. But it is not nothing. Over cosmic distances, even 0.1 atoms per cubic centimetre adds up to real pressure, and the Sun is moving through this medium. Our entire solar system orbits the galactic centre at about 490,000 miles per hour. From the Sun's reference frame, the interstellar medium is a headwind. Where the outward pressure of the solar wind finally equals the inward pressure of that interstellar headwind that is the heliopause, that is where the Sun ends and the galaxy begins. By the late 1980s, and throughout the 1990s, scientists had constructed sophisticated computer models of this boundary. They ran 3-dimensional magnetohydrodynamic simulations, incorporating real measurements of the solar wind from spacecraft near Earth, spectroscopic observations of the interstellar medium from ground-based observatories, and decades of theoretical advances in plasma physics. They refined these models over years. They had genuine confidence in what they predicted. The heliopause should be located at approximately 90 to 100 astronomical units from the Sunday. 1 AU is the average Earth-Sun distance, roughly 93 million miles. So, 90 to 100 AU meant a boundary somewhere between 8.4 and 9.3 billion miles from the Sunday, a bubble extending roughly twice the distance from the Sun to Pluto in all directions. Before reaching the heliopause, Voyager would cross the termination shock, the point where the solar wind slows from supersonic to subsonic. Models place this at 75 to 90 AU. Between the termination shock and the heliopause, a region called the heliosheath, the solar wind would slow, compress, and flow outward and sideways against the interstellar medium. Models predicted the heliosheath would be 10 to 20 AU thick. Beyond the heliopause, the transition should be clear and rapid. Solar plasma would vanish. Galactic cosmic rays would intensify. The magnetic field would rotate from the solar orientation to the galactic orientation. The whole crossing should take weeks to a few months. The heliosphere's shape should be roughly spherical, perhaps slightly comet-like, with a tail pointing away from the Sun's direction of motion, but basically symmetric. It was a coherent picture, built on solid physics, calibrated against real data. The scientists who built these models were doing their best work. Every major specific prediction turned out to be wrong. Not slightly wrong, not off by a few percent, wrong in ways that required the models to be substantially rebuilt. Wrong in ways that revealed that the inputs, the assumptions about the interstellar medium's density, pressure, and structure were critically insufficient. And wrong in ways that are still generating published research papers in 2025 and 2026. Part 3. The Breakdown. November 14th, 2023. Mark that date. On November 14th, 2023, Voyager 1 is approximately 160 astronomical units from the Sun to 14.9 billion miles. It has been in interstellar space for 11 years. It is the only spacecraft in history to have directly sampled the very local interstellar medium, the plasma, the magnetic field, the cosmic rays of the space between the stars. No replacement mission exists. No other spacecraft is en route to where Voyager is. The earliest any proposed follow-on could reach comparable distances is the 2080s. Voyager 1's data is irreplaceable. There is no alternative source. On November 14th, 2023, that irreplaceable source stops making sense. The spacecraft keeps transmitting. The carrier signal arrives at Earth right on schedule. Mission controllers at NASA's Jet Propulsion Laboratory in Pasadena can confirm the spacecraft is alive, receiving commands, responding, operating normally in the mechanical and electrical sense. But the data inside the signal is a repeating pattern of ones and zeros, the same pattern, cycling endlessly, carrying no scientific or engineering information, a meaningless loop, a stuck record. For weeks, then months, Voyager 1 continues, transmitting its meaningless repeating pattern. The mission team tries systematic troubleshooting. They attempt to restart the flight data system, the computer responsible for packaging data before transmission. They send different command sequences. They switch between backup systems. They ask the spacecraft to run diagnostic routines. Nothing works. Understanding why the breakdown was so difficult to diagnose requires understanding the communication environment. A signal from Voyager 1 travels at the speed of light. Even at that speed, it takes 22.5 hours to reach Earth. Any command takes 22.5 hours to arrive. Any response takes another 22.5 hours to return. The minimum time for any command and response cycle is 45 hours. 45 hours, nearly 2 full days, to find out if a single command worked. In early March 2024, after months of conventional troubleshooting had failed, the team tried something different. They sent a command called a poke, an instruction, telling the flight data system to dump a complete readout of its own memory. Everything, every bit, in whatever format it could manage. The command left Earth at the speed of light on March 1st. 22.5 hours later, it reached Voyager 1, 15 billion miles away. The spacecraft processed it. 22.5 hours after that, the response arrived at Earth. On March 3rd, 2024, an engineer sat down to decode what came back. The signal was not in any expected format, but it contained structure, pattern, information encoded unusually, but real. Hours of manual decoding later, a complete memory dump. A full readout of the flight data system's 68 kilobytes, bit by bit. And inside that dump, a single failed chip. One memory chip inside the flight data system containing critical operating code, the software that tells the computer how to package science and engineering data into a transmittable stream. That chip was no longer functioning. Its bits were stuck in a fixed pattern, dead. About 3% of total FDS memory. But 3% of the right memory is enough to collapse everything. A computer cannot package data if the packaging code is gone. Every reading from every instrument on Voyager 1 was being collected, processed internally, and then assembled using corrupted instructions into the meaningless pattern that had been arriving at Earth for 5 months. 2 theories for how it died. First, simple wear. The chip had been running continuously for 46 years. Nearly half a century of radiation, temperature cycling, and stress in conditions no laboratory could replicate. An accumulated damage threshold finally crossed. Second, a cosmic ray. In interstellar space, outside the heliosphere's protection, galactic cosmic rays, protons and nuclei carrying millions to billions of electron volts stream continuously through the spacecraft. A single high-energy particle passing at exactly the right angle through exactly the right location in a memory cell can permanently flip a bit, lock it in one state forever. A particle fired from a supernova explosion thousands of light-years away, travelling through interstellar space over thousands of years, arriving at Voyager 1 at precisely the right trajectory to destroy a specific 256-bit block of memory in the flight data system of the only spacecraft ever to operate in interstellar space. The universe is not aiming at us, but randomness, given enough time and enough exposures, produces specific outcomes. The chip could not be repaired. No one could go out there. The only solution was surgery. The team identified the dead chip's code. They mapped every reference to that code throughout the remaining memory. They sliced the code into fragments and distributed those fragments across unused corners of the FDS, tiny pockets of empty space scattered throughout the system. They updated every pointer in every other part of the code so the computer could find the fragments and execute them as a whole. To make room, they deleted old code. software from the Jupiter flyby of 1979, routines that hadn't been called in 40 years, still occupying bytes, unchanged since a time when disco was still on the radio. On April 18th, 2024, they sent the first batch of relocated code. 22.5 hours later, it arrived. 22.5 hours after that, on April 20th, the team gathered in a conference room at JPL to watch the response come in. For the first time in 5 months, the data was clean. Real numbers, real readings. The quiet, vital signs of a spacecraft that had, against all reasonable expectation, survived. By June 2024, all 4 remaining science instruments had resumed transmitting. The data was flowing again, and what it contained was alarming in ways the memory chip crisis never was. Part 4. The machine that refuses to stop. Before diving into what Voyager is discovering, we need to spend a moment on the machine itself, because the technology is part of the alarm. Each Voyager spacecraft has 3 onboard computer systems. The computer command system handles instructions from Earth. The flight data system, the one that failed in 2023, collects science and engineering data and packages it for transmission. The attitude and articulation control system manages orientation, keeping the antenna pointed toward Earth. Together, these 3 systems contain approximately 68 kilobytes of memory. Total. Your mobile phone contains several hundred billion times more. A $2 USB drive holds tens of millions of times more data than both Voyagers combined. The computers use assembly language, the most primitive programming level, written directly in the binary instruction set of the processor. Every line of code was written by hand in the early 1970s by engineers who are now retired or deceased, for processors no longer manufactured, using development environments that no longer exist. Maintaining this code requires learning a programming language and processor architecture not taught anywhere in formal education today. New engineers apprentice with experienced ones, absorbing knowledge never fully documented in any form a modern reader would recognize. The expertise of how to maintain Voyager lives partly in the code, partly in aging documents, and partly in the minds of people who have spent careers with it. Power is the relentless constraint. Voyager 1 launched with 3 radioisotope thermoelectric generators, each containing pressed plutonium-238 oxide spheres. Plutonium-238 decay generates heat. Thermoelectric converters turn that heat into electricity. At launch, the RTGs produced approximately 470 watts. Plutonium-238 has a half-life of 87.7 years. The thermocouples degrade independently. Combined effect, power loss of approximately 4 watts per year, every year, without exception. In 2026, Voyager 1 generates approximately 249 watts, less than 3 standard 100 watt light bulbs. Every system on the spacecraft draws from that budget. The computers, the transmitter, the 2 remaining science instruments, the heaters keeping critical components from freezing in the minus 455 degree Fahrenheit void. The margin between what Voyager has and what it needs is measured in single digits of watts. The cameras went dark in 1990. Science instruments have been decommissioned one by one. Heaters for non-critical subsystems have been switched off, letting components freeze to temperatures below their designed minimums. In 2020, the heater for Voyager 2's cosmic ray instrument was turned off, dropping it to minus 4 degrees Fahrenheit, 40 degrees below its rated minimum. It kept working. 1970s. Engineering. Running colder than it was ever supposed to. Still working. In the fall of 2024, after the memory chip crisis was resolved, Voyager 1's X-band radio transmitter shut down unexpectedly after a fault protection circuit activated. Engineers spent weeks coaxing it back online with 4-5-hour feedback cycles. It recovered. But every major system is now what engineers call single string. No backup, no redundancy, no second option. In September 2024, the team performed a thruster swap, switching from clogged attitude control thrusters to a backup set dormant since 2018, 6 years in interstellar space. The backup thrusters fired. They worked. In 2025, the backup thrusters showed signs of clogging faster than expected. Engineers began modifying software to reduce thruster firing frequency, trading pointing precision for slower fuel consumption. Every solution creates a new constraint. Every workaround introduces a new risk. Engineers playing chess against entropy, and entropy never runs out of moves. Todd Barber, a propulsion engineer on the Voyager mission, described the work in a 2024 interview as palliative care. Not repair, not maintenance. Palliative care. The careful, patient management of something living beyond its expected time, not trying to cure, but trying to keep functional for as long as it can hold on. By 2026, 2 instruments remain fully operational: the plasma wave subsystem and the magnetometer. Those 2 instruments are the eyes and ears of everything that remains. And what they are seeing and hearing in interstellar space right now is where the alarm truly begins. Part 5. Alarming discovery. Number 1. The boundary is billions of miles from where it should be. The models predicted the heliopause at 90 to 100 astronomical units. Voyager 1 crossed the heliopause on August 25, 2012. At 121 astronomical units, 121, 11.2 billion miles from the Sunday, the discrepancy was 20 to 30% beyond the most generous model estimate, approximately 2 to 2.8 billion miles farther than the most sophisticated simulations ever calculated. For a boundary defined by pressure equilibrium where the solar wind's outward push exactly balances the interstellar medium's inward resistance, a 20 to 30% error is not a rounding mistake. It is a statement that the inputs were wrong. Either the solar wind is stronger than models assumed, or the interstellar medium is less dense than models assumed, or both. Analysis after the crossing pointed primarily toward the interstellar medium. The gas in our specific local corner of the galaxy appears measurably less dense than models predicted. Not dramatically less dense, but enough. A difference that compounds over billions of miles to shift the equilibrium point outward by billions of miles. This matters because the heliosphere is a shield. Galactic cosmic rays, high-energy particles from supernovae, and other violent events across the Milky Way are significantly reduced in intensity inside the heliosphere. A larger heliosphere means better shielding. If the boundary is 20 to 30% farther than predicted, then Earth has been more protected throughout its history than we calculated. Every estimate we have made of Earth's historical cosmic ray exposure based on models that got the heliosphere's size wrong needs to be revisited. Cosmic ray flux affects atmospheric chemistry. It produces radioactive isotopes recorded in ice cores and ocean sediments as a geological record of past radiation levels. It may affect cloud formation and climate. Over billions of years, it shaped the pace of mutation and evolution. Every one of those estimates rests on a number the size of the heliosphere that Voyager proved wrong. Then there is the shape. Voyager 2 crossed the heliopause on November 5, 2018, at 119 astronomical units. Voyager 1 crossed at 121 AU. The 2 spacecraft were traveling in very different directions. Voyager 1 toward the nose of the heliosphere, Voyager 2 toward the flank. Models predicted these crossings should happen at very different distances. The nose, compressed by the sun's motion through the interstellar medium like a bow wave, should be significantly closer. The flank should be much farther. Prot. Instead, both spacecraft crossed at almost exactly the same distance. The heliosphere's shape is not what was predicted. Not a sphere, not a simple comet, something more complex, a structure being sculpted by forces the models underweighted or omitted entirely. No existing model, as of 2026, fully reproduces what Voyager measured. This is alarming discovery number 1. The boundary is billions of miles from where it should be. Its shape is wrong. And every calculation, depending on knowing where that boundary sits, needs to be revisited from the beginning. Part 6. Alarming discovery. Number 2. The transition that took years, not weeks. The models predicted the heliopause crossing would take weeks to months. A defined event. A clear, sharp transition. What Voyager experienced was a process that took more than 2 years. Starting in 2010, 2 full years before the actual crossing, Voyager 1 began detecting rising levels of galactic cosmic rays while still surrounded by solar plasma. It was still in the heliosheath. But something was changing. Cosmic ray intensity was climbing. The boundary was becoming porous in ways the models had not predicted. Then in June 2012, Voyager 1 detected something that had no name. No model had predicted it. No simulation had produced anything like it. A region where magnetic field lines were aligned perfectly and radially pointing straight outward from the Sun, organized with a mathematical cleanliness that contrasted starkly with the turbulent, tangled heliosheath field, and where particles were flowing freely along those field lines in both directions simultaneously. Solar particles moving outward toward interstellar space. Galactic cosmic rays moving inward toward the Sunday. The field lines were open in both directions, acting as channels connecting the heliosheath directly to interstellar space. Scientists called it the magnetic highway. Nothing in the prior scientific literature described a structure like this. The magnetic highway appears to result from magnetic reconnection, a process where field lines from two different magnetic domains merge at specific points, creating topological connections between otherwise separate regions. The Sun's field lines and the galactic field lines just outside the heliopause at specific locations and times appear to merge and create open channels through the boundary. Voyager 1 spent roughly 2 months traversing this highway, recording anomalously high cosmic ray intensities and anomalously low solar particle densities before ever crossing the heliopause in the plasma sense. Then on August 25, 2012, solar wind particles essentially vanished over a period of a few days. Galactic cosmic rays jumped to a new, steady, higher level. Except the magnetic field did not rotate. It kept pointing the same direction it had pointed throughout the heliosheath. No swing, no flip, no reorientation even as everything else changed dramatically. More than a year of genuine scientific controversy followed. Serious researchers published papers arguing Voyager had not crossed the heliopause at all because the magnetic rotation was supposed to be the definitive signature. Others argued it had crossed and the rotation simply had not occurred. A third group proposed previously unrecognized intermediate regions. Eventually, additional evidence settled it. Solar pressure waves from 2012 storms reached Voyager's position in 2013 and drove plasma oscillations detectable only in interstellar medium, not heliosheath plasma. Voyager had crossed. And the lack of magnetic rotation was coincidence. The local galactic field at Voyager 1's crossing location happened to be oriented roughly parallel to the solar field. Nature had not consulted the models. Voyager 2's 2018 crossing was fundamentally different. It completed in roughly 1 day. It did show a magnetic field rotation about 20 degrees. Not dramatic, but real. 2 crossings in different locations producing completely different experiences, revealing that the heliopause is not a uniform structure but a complex, location-dependent frontier. After both crossings, the heliopause continued to breathe. Solar pressure pulses from storms travel outward over years, reach the heliopause, and temporarily push it past the spacecraft. Voyager 1 detected solar particles briefly in August 2013, nearly a year after crossing before they disappeared again. The boundary had moved outward past it, then contracted. The edge of the solar system oscillating by several astronomical units over months. This is alarming discovery number 2. The crossing was not weeks, it was years. The magnetic highway was entirely unanticipated. The magnetic field refused to rotate. The boundary breathes in ways no pre-Voyager model could have predicted. What models drew as a line, reality reveals as a living, dynamic frontier. Part 7. Alarming discovery. Number 3. The hum that should not exist. In May 2021, a team led by astronomer Stella Koch-Ocker of Cornell University published a paper in Nature Astronomy describing something no one had known to look for. A hum, not a metaphor. An actual measurable electromagnetic oscillation, a narrow-band signal, stable in frequency, detected continuously by Voyager 1's plasma wave subsystem in every observation period from 2017 onward, without interruption. Before this discovery, scientists measured the interstellar plasma density using Voyager's plasma wave instrument only when something disturbed the plasma, specifically when solar pressure waves crossed the heliopause and drove electrons to oscillate. Those oscillations, called plasma oscillation events, allowed scientists to calculate the electron density at Voyager's location from the frequency of the oscillation. The technique worked. It provided valuable point measurements of density at specific times. But between those discrete disturbance events, scientists assumed the plasma was too thin and quiet to generate any detectable signal on its own. That assumption was completely wrong. What Ocker's team found was a background signal present at all times, not just during solar-driven disturbances. A persistent, narrow-band oscillation humming along at a frequency consistent with the plasma frequency of the local interstellar medium, undriven by any solar event, arising continuously from the interstellar plasma itself. James Cordes of Cornell, the senior author on the study, described it memorably. The interstellar medium is like a quiet or gentle rain. Solar events are lightning in a thunderstorm. But even between the lightning, the rain never stops. There is always a background, a baseline, a hum. This background hum transformed what Voyager's plasma wave instrument can do. Instead of isolated density measurements at the moments when solar events happen to drive oscillations, the persistent hum allows continuous measurement, a running record of the electron density at Voyager's location. And the continuous picture reveals something fundamental about the nature of the interstellar medium. It is not smooth. It is not the uniform, featureless void that models treated it as. It varies in density by 10 to 20% or more, on scales as small as a few astronomical units. There are regions where the gas is slightly clumped, slightly denser than average. There are voids where it is slightly thinner. There is structure, on scales small enough that the smooth medium assumption was not just an approximation, it was eliminating the very features that determine how the heliosphere is sculpted. Think about what that means for the heliosphere's shape. The boundary between solar wind and interstellar medium is determined by the pressure distribution around the heliosphere in all directions. If the interstellar medium has density variations of 10 to 20% on scales of a few AU, then the pressure pushing inward on the heliosphere varies significantly depending on direction. The heliosphere is being continuously pushed and pulled by an uneven, lumpy environment, not a uniform headwind, but a complex, spatially varying pressure field. Every model that assumed a smooth interstellar medium was missing the essential input that determines the heliosphere's actual shape. The hum's physical mechanism remains incompletely understood. Two candidate explanations exist: thermally excited plasma oscillations, where the thermal energy of electrons drives spontaneous oscillations at the plasma frequency, and quasi-thermal noise, a related phenomenon arising from random thermal motions of all the plasma's charged particles. The two have subtly different signatures, but Voyager's aging instruments cannot provide the frequency resolution needed to distinguish between them definitively. A future mission with better instruments could resolve this. There is no funded future mission en route. The discovery of the hum also implies something about Earth's biological history. The density structure of the local interstellar medium has changed over geological time, as the Sun has moved through different regions of the galaxy on its 2.25 million year orbit around the galactic center. As the Sun has traversed different regions with different densities, different magnetic structures, different cosmic ray environments, the heliosphere has changed size and shape, changing the cosmic ray flux reaching the inner solar system. Evidence of those variations is encoded in cosmogenic isotopes in ice cores, ocean sediments, and ancient rocks. Beryllium 10, carbon 14, chlorine 36. Some of those cosmic ray fluctuations correlate with periods of enhanced extinction rates, climate shifts, changes in evolutionary tempo. The interstellar medium that Voyager is measuring right now, more structured, more varied, more dynamically complex than models assumed, is the same kind of environment that has shaped life's history throughout Earth's existence. Every prior calculation about how the heliosphere responded to the interstellar medium over geological time used smooth medium models. Every one of those calculations needs re-examination in light of what the hum reveals. This is alarming discovery number 3. The interstellar medium hums with a signal no model predicted. That signal reveals a density structure that smooth models could not accommodate. The mechanism producing the hum remains incompletely understood, and the spacecraft that discovered it may not survive long enough to identify that mechanism definitively. Part 8. Alarming discovery. Number 4. The anomaly that refused to fade. In late 2020, Voyager 1's magnetometer and plasma wave instruments simultaneously recorded something familiar. An abrupt jump in magnetic field intensity, a simultaneous rise in plasma density. Both sensors registering an increase together, exactly the pattern scientists had seen before multiple times since Voyager entered interstellar space. Those prior events had a known cause. A solar storm erupts. The resulting pressure pulse propagates outward through the heliosphere at supersonic speed. Years later, it reaches the heliopause. When it hits the boundary, it acts like a piston, launching a compression wave into the interstellar medium. That compression raises the plasma density and the embedded magnetic field strength. Over months, the wave expands, diffuses, dissipates, and the readings return to baseline. The 2020 anomaly started exactly that way. Scientists looked at the solar activity records and searched for the originating event. They expected to wait a few months, watch the readings decay back to baseline, and add another entry to the catalogue of solar-driven compressions. 6 months passed. The anomaly did not decay. A year passed. The magnetic field was still elevated. The plasma density was still elevated, not decaying smoothly, not oscillating around a new level, just elevated. Persistently and stubbornly elevated, in a way the previous events had never been. Scientists scrutinized the timing and magnitude more carefully. They ran simulations of solar-driven pressure waves propagating through the heliosphere and across the heliopause, trying to match the observed anomaly to known solar events. The timing was difficult to reconcile precisely. The magnitude of the field enhancement was larger, and more sustained than solar-driven wave models readily explained. Some mission scientists began to articulate the uncomfortable question directly: did this anomaly originate with the Sun at all? This question marks a significant threshold. If the anomaly did not originate with the Sun, if it reflects something in the interstellar medium itself, then the interstellar medium has its own dynamics, its own events, its own features arising independently of what the Sun is doing. Several possibilities have been proposed. The Sun is moving through the local interstellar cloud, a slightly denser than average patch of gas, roughly 30 light-years across, through which the solar system has been passing for tens of thousands of years. The boundary of this cloud is not uniform. It has internal structures, filaments, clumps, density gradients that cannot be directly observed from Earth and that no model has resolved with sufficient precision to predict. If Voyager 1 crossed a density enhancement within the local interstellar cloud, a region where the gas is locally clumpier, the instruments would detect an elevated density that does not decay, because it is not a wave passing through the spacecraft, but a region the spacecraft is passing through. Another possibility involves the galactic magnetic field structure. If Voyager entered a region where the field is naturally stronger due to past stellar activity or galactic-scale field structures, the magnetometer would record an elevated field strength reflecting the ambient field rather than a propagating wave. The data is ambiguous, and crucially, the 2023 memory failure cut off the record precisely when the anomaly was most active and its character might have been most informative. Months of data that might have revealed whether the elevated readings were decaying, oscillating, or remaining constant were simply lost. When Voyager 1 resumed transmitting in mid-2024, the anomaly was still there. Scientists continue to analyze it. Research papers published in 2025 and early 2026 examine the turbulent structure of the very local interstellar medium during this period, but the results are cautious and inconclusive. The 2020 event remains, in the scientific literature, a partially explained anomaly. This is alarming discovery number 4. Something changed in the interstellar medium around Voyager, 1 inch, 2020, and has not returned to normal. The investigation was interrupted by a hardware failure that erased crucial data at a crucial moment. And the spacecraft capable of resolving the question is running out of instruments and power on a timeline that does not offer unlimited patience. Part 9. Alarming discovery. Number 5. What cosmic rays reveal about the galaxy's hidden architecture. Before Voyager 1 crossed the heliopause, scientists predicted the cosmic ray environment on the other side would be more intense. The heliosphere shields the inner solar system from galactic cosmic rays. Beyond the heliopause, those particles should be more abundant. The prediction was roughly right. After the crossing, cosmic ray intensity increased by approximately 10 to 20% compared to the heliosheath. This confirmed the heliosphere's shielding role, but the directional distribution where the cosmic rays were coming from was not what scientists expected. Galactic cosmic rays originate from violent events distributed across billions of light-years of galaxy, supernovae, pulsars, black hole and neutron star binaries. These sources are scattered throughout the galaxy, and the particles they produce have been traveling through the interstellar medium for millions of years, scattering off magnetic field irregularities, deflecting countless times, changing direction repeatedly before arriving at Voyager's location. After millions of years of scattering and redirection, the particle population should be isotropic, arriving equally from all directions, no preferred orientation, no enhanced or diminished intensity from any region of the sky. Instead, Voyager detected clear directionality, more cosmic rays from some directions than others, an asymmetry, what physicists call anisotropy, that reveals structure in the local galactic magnetic field that the scattering process had not erased. The most counterintuitive finding: both Voyagers detected suppressed cosmic ray intensity from the direction of the galactic center. The galactic center is the most energetically productive region of our galaxy. The highest density of stars, the highest supernova rate, the most energetic objects, the 4 million solar mass black hole, Sagittarius A, the densest population of pulsars and neutron stars in the galactic bulge. By simple logic, we should receive the most cosmic rays from that direction. We receive relatively fewer. The working explanation hypothesis, rather than confirmed mechanism, is that the galactic magnetic field near the center is much stronger than in the outer disk where we live. Cosmic rays produced near the galactic center are accelerated to high energies and then trapped by the intense local field, spiraling around field lines, unable to propagate efficiently outward. The field acts as a magnetic bottle. Only a fraction leak out and escape to the outer galaxy. If correct, this picture has profound implications. The galactic magnetic field is not just a passive feature of the interstellar medium. It is an active architecture, an invisible infrastructure that channels, concentrates, and disperses cosmic rays throughout the Milky Way in patterns that depend on the field's structure in ways we are only beginning to map. Voyager 2, crossing the heliopause in a different direction 6 years after Voyager 1, detected similar directional anisotropy, but with different specific characteristics, enhancement from slightly different preferred directions, consistent with the two spacecraft sampling regions of the galactic magnetic field with different local orientations. As both spacecraft move deeper into interstellar space, the anisotropy pattern continues to evolve. The picture is dynamic and spatially structured in ways that cannot be fully reconstructed from two vantage points, but that are already revealing a galaxy far more architecturally organized than smooth background models predicted. The implications for Earth's biological history are not abstract. The cosmic ray flux at Earth's surface over geological time has varied. Evidence is preserved in cosmogenic isotopes: beryllium 10, chlorine 36, carbon 14 inches, ice cores, ocean sediments, and ancient rocks. Some periods of elevated cosmic ray flux correlate with increased mutation rates in the fossil record, with climate changes, with ocean chemistry shifts. Understanding the galactic cosmic ray architecture, which Voyager is now beginning to sample directly, is necessary to disentangle which of those causes was dominant during which periods. That disentanglement may eventually tell us something important about the relationship between our cosmic environment and the history of life on Earth. This is alarming discovery number 5. Cosmic rays do not arrive uniformly from all directions. The galactic center appears to trap its own particles behind its own magnetic field more efficiently than models predicted. The galaxy's cosmic ray architecture is structured, directional, and consequential for the biological history of every planet in the Milky Way. Part 10. Alarming discovery. Number 6. The field that refused to cooperate. Of all the predictions scientists made about the heliopause, the one stated with the greatest confidence was the magnetic field rotation. Inside the heliosphere, the Sun's magnetic field dominates. It runs generally radially outward from the Sun, twisted into a spiral by the Sun's rotation and tangled further by the turbulent heliosheath. This field has a clear solar character. Beyond the heliopause, the galactic magnetic field takes over. The galactic field has been shaped over billions of years by the dynamics of the Milky Way stellar winds, supernova shocks, galactic rotation, the accumulated electromagnetic history of the entire galaxy. Its direction reflects the large-scale structure of the spiral arms. That direction should be measurably different from the solar field at the heliopause. The crossing should produce a clear magnetic rotation, a definitive signature. On the 25th of August 2012, Voyager 1 crossed the heliopause. The field did not rotate. What happened instead was continuity. The magnetic field kept pointing in the same direction it had pointed throughout the heliosheath. Solar particles vanished. Cosmic rays surged. But the field orientation, which should have been the most unambiguous signature of the crossing, was unchanged. More than a year of genuine scientific debate followed. Researchers who had spent careers predicting the magnetic behavior at the heliopause found themselves arguing in peer-reviewed journals about whether their own predictions had been fulfilled or violated. The disagreement was not about the data. The magnetometer readings were clear and unambiguous, but about what the data meant. Eventually, the crossing was confirmed through independent evidence, and the explanation for the missing rotation emerged: coincidence. The local galactic magnetic field, at the specific location where Voyager 1 crossed the heliopause, happened to be oriented approximately parallel to the solar field at the boundary. Not because of any physical connection, simply because the galaxy's field pointed a particular way at that particular location in three-dimensional space. Stamatios Kramigis, a physicist who had worked on Voyager since the mission's beginning, put it directly: nature had not read the theorists' papers, and did not know it was supposed to change the magnetic field direction. Voyager 2's 2018 crossing detected a field rotation of approximately 20 degrees, real and measurable. Less than models predicted, but real. Two crossings in different locations, separated by 24 AU, producing completely different magnetic experiences. The galactic field varies in direction on scales of tens of astronomical units or less, even in the region immediately outside the heliopause. In subsequent years, Voyager 1's magnetometer continued tracking the field direction in interstellar space. Research by Nathan Schwadron and colleagues, published in the astrophysical journal Letters, found that the field direction around Voyager 1 has been slowly rotating since 2012. Year by year, degree by degree, it is turning toward the direction that NASA's IBEX satellite, the Interstellar Boundary Explorer, had determined from remote observations to be the undistorted interstellar magnetic north. The interpretation is that the region immediately outside the heliopause is magnetically disturbed. The heliosphere's presence distorts the surrounding galactic field, like a large object deforming a magnetic fluid around it. The distortion extends for some distance outward from the heliopause. Voyager 1, now more than 50 AU beyond the heliopause, may only be approaching the outer edge of that disturbed region. The pristine galactic field, undistorted by our Sun, may be farther out still. If the heliosphere's magnetic influence extends significantly into interstellar space, more than 50 AU beyond the plasma boundary, then the Sun's domain is larger, in the magnetic sense, than the heliopause suggests. The heliopause marks where the solar wind plasma stops. But the Sun's magnetic fingerprint on the surrounding interstellar medium persists far beyond that boundary, slowly fading as distance increases. The Sun does not simply stop at 121 AU, it fades, gradually, asymmetrically, over a region of space that may extend for hundreds of astronomical units in some directions. This is alarming discovery number 6. The galactic magnetic field refused to rotate at the heliopause. The heliosphere's magnetic distortion of the surrounding interstellar space extends far beyond the plasma boundary. The extent of that distortion is not yet known, and a spacecraft now in its 14th year of interstellar travel may still be measuring a field that reflects the Sun's influence rather than the undistorted galaxy. Part 11. Alarming discovery. Number 7. The light day threshold and what follows: silence. In November 2026, Voyager 1 will reach 1 light day from Earth. 1 light day, the distance light travels in 24 hours, approximately 25.9 billion kilometers. No human-made object has ever been this far from its creators while still operational. No signal sent from Earth has ever taken a full day in each direction to reach an active spacecraft. At 1 light day distance, the minimum round-trip communication time for a single command and response cycle is 48 hours. If something fails and engineers need to run 10 diagnostic commands, each requiring a full round-trip response before the next step can be designed, the diagnostic alone takes 20 days. Before any fix is even attempted. This constraint gets harder every year as the distance grows. The 2, and a half-hour, one-way delay of today will be 24 hours in November 2026, then 25, then 26. Each year adds approximately 45 minutes to the one-way delay, as Voyager continues moving at 38,000 miles per hour. Meanwhile, the power budget does not pause for milestones. 4 watts per year, every year, inexorably. In 2026, the margin between Voyager 1's power output and its minimum operational needs is measured in single digits of watts. In the best case, no additional hardware failures, no unexpected thruster issues, no transmitter faults. Voyager 1 may sustain at least one science instrument into the late 2020s, or possibly the early 2030s. The magnetometer and the plasma wave subsystem are the last 2 instruments. At some point, there will not be enough power to run both. Engineers will shut one down. Then, later, there will not be enough to run one instrument and the transmitter simultaneously. The last instrument will be decommissioned. When that happens, Voyager 1 will still transmit but only engineering data. Temperatures, power levels, thruster status. The stripped-down vital signs of a spacecraft still alive in the mechanical sense, but no longer observing the universe. This phase may last until the mid-2030s, if RTG projections are optimistic. Then the power will fall below what the transmitter requires. The deep space network antennas will be pushed to maximum sensitivity. Signal processing algorithms will be pushed to their limits, filtering the noise of the universe for Voyager's frequency. Engineers will use every technical resource available to extend the detection window by weeks or months. Eventually, the signal will drop below the noise floor. No explosion, no crash, no drama. Just silence. The spacecraft too far away, too power depleted, too small against the cosmos to be heard any longer. And then it will drift, for thousands of years, tens of thousands, hundreds of thousands, through the outer edges of the magnetically disturbed region beyond the heliopause, through varying densities in the local interstellar cloud, passing clumps and voids in the plasma that its instruments will not be present to detect. In approximately 40,000 years, Voyager 1's closest approach to another star, Gliese 445, a red dwarf in the constellation Camelopardalis. The closest approach will be 1.6 light-years, not close enough to enter the star system, not close enough for any meaningful gravitational interaction. A slow, silent drift past a dim point of light. And then onward, into the galaxy, into the orbits of stars, into a future so remote that the Sun itself will have changed significantly before Voyager completes even one orbit of the galactic center. The golden record will still be there. Gold plating does not corrode in vacuum. The grooves in the copper disk are physical structures, microscopic valleys and ridges encoding audio information in the amplitude of the groove walls. No power required. No electronics needed. As long as the disk is not physically damaged, the information will be intact. Sounds of a living planet, the heartbeat of a human being, thunder and rain and humpback whales and laughter, and Bach and Beethoven and Chuck Berry. Greetings in 55 languages, some already ancient when Voyager launched. Images of DNA and sunsets and the blue Earth from space, encoded in the physical structure of the disk, waiting for a reader who will almost certainly never come. Carl Sagan knew this. The probability of the record being found is as close to 0 as any probability gets. He built it anyway, because the record was for us. It was the answer to the question that no model predicted and no simulation could produce. If we could say one thing about ourselves to someone who knew nothing about us, what would we say? The golden record is a civilization's answer to that question, sealed in gold, sailing into the dark forever. And the data that the spacecraft carrying that record has sent back the 7 alarming discoveries still being analyzed, still being argued over, still being incorporated into models that keep needing revision, That data is the other message, the one directed not outward at hypothetical aliens, but inward, toward us. What Voyager says to us from 16 billion miles away, across 23 hours of light-speed travel, decoded from 1/quintillionth of a watt, is this: you were wrong, not because you were careless or incompetent, because the universe at the edge of your solar system is more complex, more structured, more dynamically alive, and more consequential for the life on your planet than any model built without direct measurement could capture. And you need to know that. This is alarming discovery number 7. Not a measurement or a data anomaly, an alarm of a different register, existential rather than scientific. The most irreplaceable scientific instrument currently operating in interstellar space is dying on a timeline that permits no rescue and no delay. The questions it has opened are not yet answered. The instruments needed to answer them are powering down, and the window of direct measurement that Voyager represents is closing, 1 watt at a time, 1 year at a time. The silence, when it comes, will be permanent for a very long time. Part 12. What the planets taught us, and why the interstellar surprises are harder. Before Voyager became an interstellar probe, it was a planetary explorer, and the planetary phase 1979 to 1989, from Jupiter to Neptune, was the phase that made scientists confident. The phase that made the prediction of the interstellar boundary seem like a natural extension of a successful scientific program. At Jupiter, the confidence was justified. The Great Red Spot revealed its structure as a giant anticyclone, rotating counterclockwise, rising 5 miles above the surrounding cloud tops. Lightning erupted in the atmosphere bolts, releasing 1,000 times more energy per strike than terrestrial lightning, photographed from close range for the first time. Auroras blazed at both poles, powered by the most intense magnetic field of any planet in the solar system. And Io was the revelation that changed everything. Scientists had modelled Io as a cold, dead world, geologically quiet, like Earth's moon. Navigation engineer Linda Morabito, analysing targeting images for spacecraft position calculations, noticed something that had no business being there: an umbrella-shaped plume rising from Io's limb. An eruption, the first active volcanism ever discovered beyond Earth. The physical reason: tidal heating. Jupiter's enormous gravity, combined with the orbital resonances of neighbouring moons Europa and Ganymede, constantly flexes Io's interior, generating heat through friction enough to melt rock and drive continuous eruption. The models had not given tidal heating adequate weight as an energy source for planetary geology. The discovery rewrote the energy budget of the outer solar system. The cascade of implications was immediate. Europa showed a smooth, cracked ice surface with almost no craters, a young, continuously renewed surface. The same tidal forces driving volcanism on Io might be keeping liquid water beneath Europa's ice shell, a subsurface ocean, a place where liquid water might exist in the outer solar system, far beyond the classical habitable zone. That single inference drawn from Voyager's images and the physics of tidal heating transformed astrobiology. Life does not require proximity to a star. It requires liquid water and energy. Tidal heating can provide both, around gas giants throughout the universe. The search for life expanded, in one moment, from the surfaces of rocky planets in stellar habitable zones to the subsurface oceans of icy moons throughout the galaxy. The planetary discoveries worked. The models were broadly right. The physics was sound. And when Voyager got something wrong or left something unexplained, there were follow-up missions. Galileo at Jupiter, Cassini at Saturn, New Horizons at Pluto. Europa Clipper now en route that could correct and extend the record. The heliosphere and interstellar medium do not have that luxury. Unlike a planet, which can be revisited by successive missions over decades, the interstellar medium can only be directly sampled by a probe that is actually there. No telescope can probe the interstellar plasma density with the resolution that Voyager's plasma wave instrument achieves. No remote observation can detect the persistent hum. No distant measurement can characterize the 2020 magnetic anomaly with the detail needed to distinguish solar from non-solar origin. And unlike the planetary missions where a wrong prediction could be corrected within years by a new spacecraft, a wrong prediction about the interstellar medium waits decades for correction. The proposed interstellar probe mission, even if approved today and launched in the early 2030s, would not reach the heliopause for roughly a decade after launch, and would not reach regions comparable to Voyager's current position for several decades after that. The interstellar surprises are harder because they are slower, because the feedback loop between prediction and measurement is measured in decades, because the only instrument currently capable of providing correction is almost out of time. The planetary phase showed what exploration looks like when you have the luxury of follow-up. The interstellar phase is showing what it looks like when you do not. And the 7 alarms Voyager is raising, the hum, the anomaly, the magnetic field, the boundary location, the cosmic ray directions, the breathing heliopause, the dying power budget. These are alarms that may not be fully answered for a generation. Part 13. The people who listen. There is a human dimension inside the technical story that deserves its own moment. The engineers and scientists who maintain Voyager today are, in many cases, younger than the mission itself. People born after Voyager launched are writing assembly language patches for its computers. People who were in elementary school when Voyager crossed the heliopause in 2012 are now analysing its magnetometer data and publishing papers in astrophysics journals about the structure of the local interstellar medium. Suzanne Dodd, the Voyager project manager at JPL, spoke about this in 2024. She noted that younger engineers are coming onto the team and contributing in ways that sometimes find solutions the more experienced engineers had not considered. People who did not grow up with the assumption that certain things cannot be done, and who therefore sometimes find ways to do them. The Deep Space Network, the system of 3 massive radio dish complexes in California, Spain, and Australia that make communication with Voyager possible, has been tracking these spacecraft for nearly half a century. The 230-foot dishes were built partly for Voyager and its predecessors, upgraded over decades to handle the growing distances and shrinking signal strengths, and are now maintained partly to continue receiving signals that are already so faint that receiving them at all is an engineering achievement. The signal that arrives from Voyager 1 measures approximately 1 quintillionth of a watt. That number is difficult to make concrete. The faintest signal that human technology routinely decodes, yet the Deep Space Network reliably extracts real scientific data from it every time the spacecraft transmits. Todd Barber, the propulsion engineer who called the Voyager maintenance work palliative care, he has spoken about watching the thrusters fire in 2025. Thrusters dormant since 2004, sitting for 21 years in the cold of interstellar space, and finding, to everyone's relief, that they worked. There is a quality in that relief that is not purely professional. Something was saved that should not have survived. And it survived. There is something particular about the experience of working with a signal that left its source 23 hours ago and has been travelling at the speed of light ever since, through interstellar space, to arrive at a dish in the California desert as a whisper barely distinguishable from the universe's background static, and inside that whisper, data, real measurements, from the only instrument in history positioned to make them. The signal keeps coming, the data keeps arriving, the scientists keep analysing. Some of what they find is expected, some of what they find is alarming. All of it is irreplaceable. Part 14. What comes next and why it matters that we begin. The proposed interstellar probe mission represents what the scientific community has recognised it needs: a purpose-built successor to Voyager's interstellar science program. The concept calls for reaching 500 to 1,000 astronomical units within 50 years of launch, 5 to 10 times farther than Voyager's current position using a close solar flyby gravity assist to. Achieve cruise speeds 2 to 4 times faster than Voyager. At those distances, an interstellar probe would sample regions of the interstellar medium far beyond the magnetically disturbed zone near the heliopause. It would carry modern plasma wave instruments capable of resolving the hum mechanism modern systems with frequency resolution sufficient to distinguish thermally excited oscillations from quasi-thermal noise. It would carry more sensitive magnetometers capable of mapping field structure over larger regions. It might carry a camera capable of imaging the heliosphere from outside, seeing the sun's bubble as a whole object, from a vantage point no instrument has ever occupied. The mission remains unfunded and unscheduled. Scientific advocacy has been strong and sustained. Multiple decadal surveys have identified interstellar science as high priority. But consensus does not equal budget. The scientists currently in their 30s advocating most actively for this mission will be in their 70s or 80s before it delivers its primary science results. They know this. They advocate anyway. Because the alternative, no mission, no follow-up, no correction of the alarming discrepancies that Voyager has revealed, is worse than beginning something whose conclusion they will not live to see. This is the particular form of courage that deep space science requires, not the courage of the moment, the courage of the long view. The willingness to begin something important precisely because it is important, regardless of whether the person beginning it will witness the ending. Voyager itself was built by people who held that courage. The engineers and scientists of the early 1970s knew that the interstellar phase of the mission, if it happened at all, would unfold long after most of them had retired. They built the spacecraft robust enough to last, choosing simplicity over sophistication, redundancy over capability, durability over feature richness, because they understood that the most important discoveries might come from a machine they would never update, communicating from a distance they would never traverse. Their gamble paid off in ways they could not have predicted. The magnetic highway, the plasma hum, the persistent anomaly, the boundary billions of miles from where the models placed it. None of these were in any proposal or prediction document from the 1970s. They are the discovery of exploration, the finding of what you did not know you did not know. What Voyager has demonstrated, over nearly 5 decades, is what it looks like to build something with enough integrity and robustness to outlast its own expectations, and to keep reporting faithfully from places no human vision reaches. That is the model for what comes next. The data that Voyager has sent back everything already in NASA's archives will be studied for decades after the last signal fades. Researchers not yet started in their careers will find correlations no one has yet noticed. Theoretical models not yet written will be calibrated against Voyager's measurements of the interstellar medium, the magnetic field rotation, the persistent hum, the 2020 anomaly. The knowledge does not end when the transmission ends. But there is something irreplaceable about a working instrument at the location, about measurements made now, during this specific passage through this specific region of the local interstellar cloud, at this specific moment in the Sun's journey through the galaxy. Every year of continued operation is irreplaceable. Every watt the RTGs manage to sustain. Every instrument that refuses to die in the cold. Every transmission the Deep Space Network decodes from 1/quintillionth of a watt. Part 15. The Last Signal. Here is what we know about how this ends. There will be a day in the late 2020s or early 2030s when there is not enough power to run a science instrument and the radio transmitter at needed levels simultaneously. Engineers will have seen it coming. They will have been managing toward it for years, watching the budget, conserving where they can, hoping the margin stays positive one more month. When the moment arrives, they will make the choice they have been deferring. One instrument, the magnetometer or the plasma wave subsystem, will take its final reading. The data will be packaged by the flight data system, passed to the transmitter, beamed toward Earth at the speed of light. The signal will cross 16 billion miles or more. It will arrive at the Deep Space Network antenna 23 or 24 hours later. Engineers will decode it. They will know, decoding it, that it is the last. And then the next transmission will contain only engineering data, temperatures, power levels, thruster status, the quiet, stripped-down vital signs of a spacecraft alive in the mechanical sense, still receiving commands, still capable of reporting its own health but no longer reporting on the universe outside. This phase may last years, then the power will fall below what the transmitter requires. Engineers will push the Deep Space Network dishes to maximum sensitivity. They will filter the cosmic radio background with every technique available, listening for Voyager's carrier frequency in the noise of the universe. They will find it for a while, then they will not find it anymore. No announcement, no ceremony, just a point in time when the signal that's been arriving reliably for nearly 50 years is no longer there. The spacecraft will not have ended. It will still be traveling at 38,000 miles per hour, as it will continue to do for as long as the universe exists. No friction in the void between the stars, No resistance, no slowing. Just motion perpetual and invisible and alone, carrying its golden record through interstellar space for timescales that dwarf any human frame of reference. In 40,000 years, Voyager 1's closest approach to another star, Gliese 445, 1.6 light-years. Not close enough for any encounter. A slow, silent drift past a dim red point of light. And then onward, into the galaxy, into the orbits of stars, into a future so remote that the Sun itself will have changed significantly before Voyager completes even one orbit of the galactic centre. The golden record will still be attached. Sounds of a living planet, a heartbeat, thunder and rain and wails and laughter and Bach and Beethoven and Chuck Berry. Greetings, in 55 languages, images of DNA and sunsets and the blue Earth from space, encoded in the physical structure of a gold-plated copper disc, waiting for a reader who will almost certainly never come. And the data that the spacecraft carrying that record has sent back the 7 alarming discoveries being analysed right now in 2026 by scientists sitting at computers receiving transmissions from 16 billion miles away that data is the real message. Not to hypothetical aliens, to us. What Voyager says to us, from 16 billion miles away, across 23 hours of light-speed travel, decoded from 1/quintillionth of a watt, is this. You were wrong. The models you built with confidence were wrong about the distance, wrong about the shape, wrong about the transition, wrong about the plasma, wrong about the field, wrong about the cosmic rays. Wrong in ways that matter for understanding where we live in the galaxy and how that galaxy has shaped the life that evolved on our planet. And you need to know that, not because being wrong is shameful, but because being wrong after a genuine, rigorous, good-faith attempt to be right is what exploration looks like. It is what discovery requires. You make the best model you can from the data available, you send an instrument to test it, and you find out what was missing. The wrong predictions are not failures. They are the points of entry into what you did not know you did not know. Voyager's greatest gift, greater than any single discovery, greater than the detection of the magnetic highway, or the measurement of the plasma hum, or the documentation of the persistent anomaly, is the demonstration that the universe is always more complex, more structured, more interesting, and more alive with unexpected phenomena than any model built before direct measurement can capture. We thought we understood the edge of the solar system. We built the models, we ran the simulations. We were wrong. We found out by sending something to look. That is the whole of science. That is the whole of exploration. That is what 2 spacecraft built with 1970s technology, running on 249 watts, using 68 kilobytes of memory, transmitting through antennas weaker than a refrigerator light bulb, still have to teach us nearly half a century after launch. They are still talking. We are still listening. The signal is still crossing 16 billion miles to reach us, 1/quintillionth of a watt, 23 hours at the speed of light, carrying data from the only instrument in history to have directly measured the space between the stars. And when it finally goes quiet, when entropy finally collects what it is owed, when the last watt fades and the last signal dissolves into the background of the cosmos, what Voyager leaves behind will not be silence. It will be questions, better questions than we knew how to ask before we sent the spacecraft to ask them. Questions about the structure of the interstellar medium, the architecture of the galactic magnetic field, the persistent hum of plasma in the dark, the anomaly that refused to fade, the boundary billions of miles from where every calculation placed it. Questions being answered right now by scientists receiving transmissions from 16 billion miles away. Questions that will still be alive in the literature long after Voyager falls silent, waiting for the next instrument brave enough to go out there and look. 2. Spacecraft. 1970s. Technology. 249 watts. 68 kilobytes. A transmitter weaker than a light bulb. Still talking. Still alarming. Still, against all odds and all expectations, still teaching. Until the day the signal fades, and the spacecraft sails on alone and silent into the eternal, humming dark. If this journey stayed with you tonight, if something in this message from the edge of everything reached across the distance and landed, Take a moment to subscribe. Leave a word in the comments. Share it with someone who still looks up and wonders what is out there. That is how this channel finds the people it was made for. We will be back, and next time we go even farther.